Right, I'd just like to introduce experiment 43, which is the determination of crystal lattice type, practical, that some of you still have to do. I won't deal with all of the prac here, I'm just going to very briefly introduce it. There's a lot of detail in the prac manual about this. Please go through this and make sure you understand all aspects of it. But the first thing that the prac addresses is how can we determine how the packing is of atoms in a crystal of the two compounds we're looking at. The two compounds are cesium chloride and lithium chloride, and they could be arranged in a primitive arrangement. So that cesium chloride is in a primitive arrangement. All the atoms are in a perfect cube, simply arranged. With lithium chloride it's slightly different, where you've got atoms of chlorine, for example, at the corners of a cube, and on the faces of the cube your lithium atoms reside. Now XRD can determine which type of packing is present in the crystal. So you'll take a powder, you'll take it to the instrument, and from the reflections, the X-ray reflections you see, you'll be able to determine the packing type. So the first substance we look at is lithium chloride. Lithium chloride is face-centered, so you've got your cube, but at each of the faces you've got a chlorine atom there. You'll notice it's cubic, so if we could determine the size of unit cell, we could then determine some interesting details about the chlorine atom. For instance, if you're going from the bottom corner to the top, you'll see that along that diagonal you fit exactly 2 chlorine atoms going down that diagonal. So if you can work out what the length of the diagonal is, you can calculate what the atomic radius is of chlorine. Don't forget that in a crystal this repeats and repeats infinitely, almost infinitely in all directions, given that atoms are extremely small. So that's the packing for lithium chloride. The packing for cesium chloride is slightly different. So here's cesium chloride. These purple atoms are cesium, and you say it very simply as a cubic arrangement. So you see the cubic arrangement for cesium. Here's the chlorine. They're also a simple arrangement in a cubic arrangement. And it's like these two primitive arrangements are interleaved with each other, so that chlorine atom is right in the center of the cube that's bounded by those cesium atoms. Okay. So with these packing types, I've got over here, this is lithium chloride going on and on for many unit cells, and you'll notice that as I rotate lithium chloride very gently, I'm just going to rotate it, you'll see that planes appear and disappear as I move it around. You'll see every now and again you'll see some different planes appear, and these are the planes that the X-rays will be reflected off, and from these reflections from these planes we'll be able to determine what the packing type is. So have a look at the Bragg manual. They'll describe the Bragg angle, and this Bragg angle is dependent on these planes that you see in the crystal. Just a note that the information you get from the instrument is always given as 2 theta, because you've got your X-ray emitter that's an angle of theta to the sample. It shines X-rays at the sample, and that then comes back to the detector, which is also at an angle of theta to the sample. And so for historical reasons the values we get are 2 theta. But if you take lithium chloride or cesium chloride down to the instrument, and we've done it with previous groups, you end up getting the XRD comes back looking like this, and you can see the different intensities where you've got a positive reflection from layers in that, and there's a 2 theta value associated with each of those layers. So how do you work this prac? Well, it's interesting that in the prac you're going to have a spectrum available to you, and what you need to do is you need to tabulate those 2 theta values, And so the easiest way to do it is to build up a spreadsheet, and in the first column have your 2 theta values coming down. But of course we don't want to deal with 2 theta, we want to deal with theta. So I advise you to simply divide by 2 in the next column of your spreadsheet. However, we can't work normally with theta in degrees, because the sign in spreadsheets and on many calculators, just be careful, often expects to have radians, so it's worth changing to radians. You simply multiply by pi and divide by 180 to change it to radians. Then you can get sine theta. Just make sure that you are calculating sine of theta. Sine of 90, for example, should be exactly 1. So just check that the sine is taking the correct input and producing the correct sine that you expect from it. Once you've got your 2 theta and your theta and your theta in radians and your sine of theta, you can then square it, and you will get a value of the square of the sine of theta, which we then take forward. Now what you want to do is we need to find some values of n. So when you divide the first sine theta by the first value of n and the second sine theta by the second n, you want to get at the end of it a constant. Now there's a table in the manual, and this is a table that's really important, because if you, for a primitive, choose n to be 1, 2, 3, 4 and 5, and you put n in the table as 1, 2, 3, 4 and 5, if these reflections are coming from a primitive type, then your sine squared theta divided by those n that you've chosen will be constant. If it's not constant, it's not primitive, and so you have to scrap those n and you have to try a different load of n's to see if they work. So if it's not primitive, try for face-centered. Try, instead of doing 1, 2, 3, 4, try 3, 4, 8 and 11. 3, 4, 8 and 11, see if it comes out constant. If it comes out constant, then you know it's face-centered. And we won't go to body-centered, because neither lithium chloride or cesium chloride are body-centered. We know that cesium chloride's primitive and lithium chloride's face-centered. So you must, from one of your spectra, from one of your lists of 2 thetas, be able to use the n for primitive and get constants, in which case you know it's cesium chloride. And for the other, you should be able to use n's for face-centered and get a constant, in which case you know it's positive. Now it's really important that constant you get out of it, because that constant is lambda squared over 4a squared. A is simply the size of a unit cell, and that will be hopefully in angstroms at the end, but it's dependent on the wavelength of X-rays that are used. Now the X-rays in our instrument are on a copper target. Electrons are fired at a copper target, and the X-rays that come off as a result are typical of copper at CK alpha, and the wavelength of X-ray is 1.54184 angstroms. You will need this value to calculate the size of a unit cell. So once you've got a table with constants in it, you can maybe explore an average for that and get an error value on that, because they will all vary ever so slightly. From that you will be able to calculate, using lambda, you'll be able to calculate the size of unit cell. So here for lithium chloride, you'll have chosen for lithium chloride a face-centered set of numbers. You'll end up with a constant. You'll be able to calculate A. And once you know A, then you know the size of a unit cell, and you can see that if this side is A and this side is A, you would be able to then calculate, if you knew the value of A, which you will know, you will be able to calculate the diagonal here. And that diagonal includes a radius of chlorine and 2 radiuses of chlorine and another radius of chlorine. So that diagonal includes 4 radiuses of chlorine, and so once you've calculated the length of diagonal, you'll be able to calculate the ionic radius of chlorine. Okay. So that's what you can do with lithium chloride. And then be careful, because you're going to have to calculate the density. If you know the length of A for lithium chloride, you will be able to do A cubed to get the volume for lithium chloride, and you will have the volume of unit cell, and that unit cell contains, and you have to think about it, it contains some atoms of chlorine and some atoms of lithium, and you can use those to calculate the mass that's in that unit cell, and you would be able to calculate the density from that. Have a look at the manual, and the manual will advise you on how many atoms of each are in the unit cell. With cesium chloride it's slightly different. You will by now at this stage know what the ionic radius is of chlorine, and so you will be able to use that in the next stage of calculation. For the next stage, once you know the A for cesium chloride, A for cesium chloride is just the length of that cube that you've got there. You're going to be exploring the diagonal now, the long diagonal, the three-dimensional diagonal from the top right corner at the front to the bottom left corner at the back. So that diagonal is in 3 dimensions. It goes straight through a chlorine atom, but I've drawn it here to make it easier to see, but really they all touch. So the top right front touches the chlorine, which touches the bottom left back cesium. So along that diagonal you've got a radius of cesium, you've got a full diameter, 2 radiuses of chlorine, and you've got another radius of cesium. So if you can calculate the distance from that corner to the reverse corner, then you would be able to subtract a diameter of chlorine to be able to finally calculate what a radius is of the cesium. And so that is what the first thing we get from that. And then of course when you want to calculate the density, you can use the A cubed for the volume of cesium chloride. And of course in cesium chloride you'll find that there is only one atom, because at each corner only 1/8 of each of these cesium atoms is in the box. Only 1/8 of that one is in, and there are 8 atoms. And of course there's one chlorine right in the middle of that box. You'll find there's only one atom of each. You'll be able to calculate the exact mass, convert the mass of one atom of chlorine and one atom of cesium to kilograms, and then divide it by the volume in meters cubed, and you'll be able to get the volume, the density of cesium chloride from that. So that's what we're trying to do here. We're trying to match the spectra to the face-centered lithium chloride. We're trying to match a spectrum to the primitive cesium chloride, and we want to then calculate from lithium chloride the ionic radius of chlorine, because it's so big in lithium chloride. And then once we know the ionic radius of chlorine, we want to calculate the ionic radius of cesium with the cesium chloride. And then finally for both systems we would like to calculate the densities. And of course the densities of lithium chloride and cesium chloride are very well known, and so you can always check your answers for the density to those that are easily available on the web.